I think it's time to get started. Pardon? You're watching your fight. I didn't know you were a fighter, boxer. You're not there yet. On the screen is the lateral directional force and moment model that we're going to be working with. So here shows let me get rid of that. There we go. Here it shows that the side force here is a function of beta the non-dimensional beta dot, P, roll rate, non-dimensionalized, R, aileron, and rudder. So those are the variables we identified a while back when we talked about which variables affected this perturbation, forces and moments. We're going to do the rolling moment and the yawing moment as well. So just like longitudinally, we're going to develop each of the columns. So the first one is CY beta, CL beta, and CN beta. And these are really easy because we really already talked about all of these. So the development goes just like the longitudinal. The total force is the coefficient times dynamic pressure times S. Total moment is the rolling moment coefficient, Q bar S B. Yawing moment is the coefficient times B. And so these are the formulas that we'll be taking derivatives of with respect to each of the perturbation variables. And these are, this lateral directional are a lot easier because if you remember, if we were looking at the longitudinal, see if I can remember this right.
I'm sorry, Professor Steck, but are you on OneNote? Because we can only see your textbook.
What did he say?
No. We cannot see you.
You can't see the shared screen?
Yeah.
Did I pick the wrong one? Maybe that's the deal here. Yes, I was still on the other one, wasn't I? You know, so now you see it, yes? Yeah, okay. Sorry, I was still on that other matrix, right? So here I've written the lateral directional side force, rolling moment, yawing moment in terms of the coefficients. And when we were back looking at the longitudinal, these were complicated by the fact that we had that angle alpha. Pretty sure I got the sign right here. That may be a minus, but I think it's a plus. Complicated by the fact that because of the stability axis versus the perturbation of alpha, the axis tilt down, and we have components of the drag and the lift in both X and Z directions. So for lateral directional, it's a lot easier. So the first thing we're going to do is just look at the beta perturbation. And we're going to say it does not affect the dynamic pressure, because the dynamic pressure depends on the velocity, and the velocity is u1 plus w squared, and then little v and little w squared. And those little v squared is where the beta comes in, and we said that was small, even back when we were talking about longitudinal. So this is easy. We just take the derivative of each of those forces. With respect to beta, beta is already non-dimensional because it's an angle in radians, so we just get cy beta q bar s. Or of course, cy subscript beta means the derivative. Same thing with rolling moment and yawing moment. And these derivatives we already discussed. In the steady state forces and moments, because we talked about how beta affects rolling moment. It's mainly a vertical tail and a dihedral effect. So we have formulas for these back earlier in chapter 3. So we're done. Except I want you to remind yourself, what's the sign on this for stability? It doesn't hurt to remember that. This is an important derivative. Cn beta. We want this to yaw into beta because that reduces it, right? A positive beta comes in from the right side. We want it to yaw toward that direction, reduces beta. How about the sign on Cl beta? So let's see, the sign here is positive. We want this to be negative. We want to roll away, because typically a beta, rolling beta, or a beta due to a roll, is the airplane banks to the right, starts to side slip to the right. We want it to roll back up right. That doesn't really have anything to do with our derivation here, but it's just a remembrance of what these static stability derivatives do. Where? This is plus. But this thing, when you calculate it, should be negative. Oh, that reminds me. Thanks for saying something. The reason I put a plus sign here, here, and here is some of the older editions had a negative sign there. My newer edition does not, but double check that. So this is on page 148. It's been corrected in most of the newer editions, but if you happen to have picked up a used or an older edition, make sure you fix that. Anybody have a book that has a negative sign there? You do? And I remember you had that other typo that I had that most other books don't have. So make sure you change it to a plus. All right, the next one is the beta dot. So again, we're going to use a non-dimensional version of this. Just like we did beta, above was non-dimensional because it's in radians. So as we take derivatives of these equations, we're going to end up with cy beta dot, cl beta dot, and cn beta dot, meaning derivatives with respect to that combination. So cy beta dot means and CL subscript beta dot means and the same thing for CN subscript beta dot. Like that. So you always have to remember that. When you look up a value for this and you multiply it by something to get the total yawing moment, for example, you need to multiply it by beta dot b over 2u1. If you go back to that matrix in the book, you'll see that automatically. So this is column 2 in that matrix. This needs a little bit more explanation, just like the alpha dot. Anybody still writing? Did I go too fast scrolling up? Let me give us a little more space here. Scroll which way? Sorry, for me, up is down and down is up. Are we good? Anybody else on Zoom still working? All right, so just like alpha dot, this is the lag in sidewash from the wing to the vertical tail. So it's really a vertical tail effect. And our sidewash model then is going to have the sidewash of beta lagged by delta t seconds. And that delta t is calculated just like before. It's the distance from the wing back to the vertical tail in the stability axis system. So xvs is the distance to the vertical tail, not the horizontal tail, and u1 is the velocity, so that's how much time it takes to get back. So, oh, and sigma 0, typically for a symmetrical airplane, this is 0, because the flow is symmetrical left and right, so you don't get a constant sidewash at 0 beta. Now, if you have an airplane with like a 182 with a propeller in the front and that air is swirling, there will be a sigma 0. So our sigma model no, not the way we're doing it. So this is So just like before, we say that beta at t minus delta t, sorry, I should have done this before I wrote that last line, is beta at t times beta dot times delta t. Right, so that's just the Taylor series thing again, where a function shifted by delta t is the function at t, and then you use the slope to go the delta t forward. Now the nice thing is that we've already developed expressions for cy, cl, and cn for the vertical tail. Because we did this when we were talking about calculating CL beta, CN beta, and CY beta. And you go, I don't remember that. Well, as I write the formula down, you'll see exactly where it comes from. So again, we're just talking about the vertical tail now, not the wing or anything else. With the side force of the vertical tail, it's the lift curve slope times the angle of attack. Then this is the sideways angle of attack, so it's beta reduced by sigma. And then we multiply by Q bar V, SV, and then it's non-dimensionalized with respect to Q bar S to get it for the entire airplane. So again, even though we maybe don't remember deriving this, it's real obvious. It's the lift curve slope times angle of attack times dynamic pressure and area. Now we need a negative sign on here, and that matches with what we did before, because a positive beta pushes on the vertical tail from the right side, and then that's in the negative y direction. Right, maybe we draw a picture. Here's the CG, vertical tail. That's a horrible vertical tail. Here's our vertical tail. Beta's coming in like this. And so it pushes that way, which is in the negative y direction. And in the same way, we take this side force and then we just multiply by the moment arm, and that gives us the rolling and yawing moment. So the vertical moment arm that creates a rolling moment is ZVS and we non-dimensionalize that moment arm by dividing both sides by Q bar S B for the moment, so that's how we get a B underneath this. And a positive beta produces a negative rolling moment if the vertical tail sticks up, which is what gives us the CL beta stability to begin with. And then for the yawing moment of the vertical tail, it's the moment arm back times the force. And I can add that XVS to this diagram. That's this moment arm here, back to the AC. And this is positive because a positive force here creates a positive yaw. Sorry, a negative force there times the XVS gives us a positive yaw. So remember, what we're wanting is the derivatives of these things with respect to beta dot. Here I am writing, yeah, now these are partial derivatives because there's multiple variables. So we're going to take the derivative of that with respect to beta dot. Well, where does beta dot show up in those formulas? This is beta, so that's not beta dot. This is just lift curve slope. That's a number, 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 number. Beta is inside here because we said so. And it really is. Here we're saying beta dot through that lag affects the side wash. So then it's just a matter of taking the derivative of each one of these equations and chain ruling and product ruling back till you get to beta dot. So we're going to get like an XVS over U1 times all of these, and that's the derivative. So for example, for CY, we're going to get CL alpha V, and then we're going to get D sigma by D beta, and then we're going to get XVS over U1 in the formula. And then the other two formulas look exactly like that, except the sign may change and the moment arm may change, but other than that, it's the same derivation. So let's do the CY derivative. So CY beta dot means this fancy derivative and we can pull that out. You can do it as terms of partial derivatives of a change of variable or however you want. We went through that when we were talking about the longitudinal. So we just need to take the derivative of the stuff up there with respect to beta dot. So for CY, we get a minus 2 U1 over B times CL alpha V times D sigma D beta XVS over U1. And then we have SP over S Q bar V over Q bar. So that's just all the stuff that goes along with the sigma up there. You guys all good with that derivative? All right, all these terms just went along for the ride. These terms came from the D sigma D beta dot. And here we say, oh, look, U1 cancels with U1 here. So again, this derivative does not depend upon how fast we're flying. It's good for most air speeds. And so that's our formula. And we can pre-calculate this. You know your lift curve slope of the vertical tail. You have an estimate of your downwash model. You know how far the vertical tail is behind the CG. You know your areas. You know how fast you're going here and the ratio. And most of the time we'll say this is 1, that the dynamic pressure is about the same. And we know our wingspan, and we know the number 2 for sure. So CL and CN beta dot look exactly like this. The only thing that's different is the moment arm. I'm going to switch away from the red here. And often we get tired, remember, of writing Q bar V over Q, so you write that as A to V. And here's where the vertical moment arm comes in. And then you go, wait a minute. This is a rolling moment. Why do we have the longitudinal moment arm here? This is the vertical moment arm, right? So that makes sense because this is the rolling moment. Where did this thing come from? It came from the lag, right? Remember, delta T was that thing. So this is from the lag. And this is from the moment arm. It's always important when you derive something as you look at the terms and you go, where did that come from? Because that seems strange. Kind of like you're wandering in the Amazon and all of a sudden a weird animal appears on the bank of the river with your canoe. And you go, where did that come from? Is it dangerous? Is it going to eat me? Is it poisonous? Not that I've ever been down the Amazon, but I used to watch the Star Trek show and all the sci-fi shows where they'd land on a planet. And of course, the guy in the red shirt always finds out that the creature that jumps out of the river kills him, right? There's a book about that called Red Shirts, if you ever want to read it. It's a novel about a fictional story where the people on board the ship discover that the red shirt people are always dying. It's not Star Trek based, it's just a fictional novel, but it's fun to, it's a good read. It's called Red Shirts. Let's do CN beta. And then we do our weird animal, maybe not so weird this time because, well, here's our moment arm. But you might say, okay, well, we got the moment arm twice. That seems wrong because it's just one moment arm times something, right? Well, where did that other one come from? Came from the lag. So it's not the moment arm twice, although the lag is because of that same distance. Yeah. See, you're doing this, look at it and go, that's weird that it shows up twice, right? But where did it come from? It came from this lag term. And it came from the fact that we had, for the yawing moment, we needed the moment arm. So you're not likely to get eaten by that weird creature. Maybe, hopefully not. All right, I need to scroll up. Anybody still working on this? So I'm going to switch to the board because some of this stuff is a good thing to demonstrate with the airplane, with the foam airplane. So let me put that together while you're working on that. While you're waiting, answer this question. What did they just discover on the moon? Yeah, I haven't switched it yet. Yeah, they found water. So you can think, well, there's underground lakes, right? it's frozen. And in fact, I was on a Zoom call with a physicist, and Dr. Behrman, I don't know if you guys had her for physics, and she was saying, well, it's actually water so dispersed into the surface and the minerals that you can't really call it a liquid or a solid or frozen. It's just present and combined with the minerals, but it's there. So you guys can, if you want to, go live on the moon in a moon base, right? That would be kind of my nightmare. I mean, it'd be cool to be on the moon maybe for a week, but if it rains for a week here and I can't go outside and do stuff, I get kind of crazy. Not crazy, but so I like to be outside. Let's see, so I'm gonna switch back now. So you should be seeing the board now. So just to remind you, we're still working on this matrix. We've done the beta column and the beta dot column. So now we're going to do the roll rate, yaw rate, aileron, and rudder. The last two are easy. So once we get through these two, we're almost done. Roll rate is a dynamic derivative, just like the pitching rate. It damps the motion. And the yaw rate damps the motion, except in longitudinal, the pitch rate was pretty straightforward. It was the horizontal tail and that was it. In this, there's coupling between roll and yaw rate, roll rate and yawing moment. And there's a coupling between yawing moment and rolling moment. So in a pitch rate pretty much damped just the pitching moment through CMQ. But here, the roll rate can be damped by, well, where do I want to see? Oh, here, the roll rate can be damped by a yawing rate, and the yawing rate can be damped by a rolling rate. So there's cross coupling, and we'll talk through all of that. So we're going to do the P, roll rate effect. So here's a P perturbation. And we always have a non-dimensional version of this because it's radians per second, so it's not non-dimensional all by itself. So the first thing I want to talk about is the side force due to yaw rate. We're just going to work our way through CY, CN, and CL and CN. And this is mainly a vertical tail effect. The wing and the horizontal tail don't play into this. So we're going to draw a big picture of the airplane. I'm going to try to make it look like this is from the front. Does that look like we're looking at the nose of the airplane? Big old vertical tail. Wow, the vertical tail is almost as big as the wing. So label this front view. And before we draw anything more on this diagram, let's look at the airplane. So here's our airplane, and we're talking about it rolling. So it's doing this thing. Now you can see the wings are going to be sweeping through the air, but that doesn't create a side force. It's going to create a rolling moment. Same deal with the horizontal tail, but with the vertical tail, it's rolling around so that there's a relative wind that's going to be hitting it this way. Because, I mean, it's still flying forward, but as it rolls, it's going to generate a side force in that direction because of the roll rate. And that side force is going to be dependent upon how far up the aerodynamic center is and how fast it's rolling. Make sense? So we get a side force in this direction. And we're going to get a yawing moment like this. And we're going to get a roll like that. All from the P. So we're going to walk through those. And that's the side force rolling moment and yawing moment of the vertical tail. But for the rolling moment and yawing moment, the wings also come into play. But the side force, you don't get much of a side force from the airplane doing this. And once we do this derivation for the vertical tail, we just multiply by the appropriate moment arm and we get the rolling and yawing moments. All right, so here's a front view. Positive roll rate is like that. Double check that. Thumb out the forward x-axis. Fingers give us positive roll. Right wing down, right? So far, so good. So the aerodynamic center of the tail is moving that way. I think I did that the wrong way, didn't I? Let's go back to that in a minute. So we get a side velocity. That's the distance ZVS up, and it's rolling like that. So we get, because this is going this way, we get a side force in the negative direction. So did I do that wrong? Yeah, I did. So we're rolling like this, right? This is sweeping this direction, so we're going to get a force resisting that motion that way. Everybody good now? This is rolling positive like that, relative wind this way, that's going to push on the vertical tail in that direction. Pardon? What's going? Yeah, the vertical tail is moving that way. So then there's a relative wind coming in this way. Call it delta V infinity coming in that way. So I'm trying to draw the motion of the tail there, which creates then a relative wind coming in the opposite of it. And so we can calculate a delta angle of attack of the vertical tail as that side velocity divided by the forward velocity. All right, so that's the little component of the side velocity vector. And then you have the forward component, and then we're saying tangent and sine are just the angle. So this is the effect. P gives us this delta alpha of the vertical tail, and that's what gives us the side force. So again, lift curve slope of that flying surface. We have the normal angle of attack of the vertical tail, which is minus beta plus sigma. But we don't care about that now. We're just looking at the P version, the P effect. And so make sure you put Q bar V, SV there. And so that's where P shows up, is PZVS over U1. So that's, if you take the derivative of this, with respect to P, that's where you get the P derivative. So we have to convert this. We're doing this in terms of force, so we have to convert it to a coefficient by dividing by Q bar S. And so then we can take the derivative. I'm not going to write that whole thing again, so that's what goes in there. And that's what goes in there. And so the derivative with respect to P just gives us this term here. And I lost my minus sign, didn't I? Nope, it's there. I lost it here. No, I guess not, because I said this whole thing gets shoved in there with the minus sign. Okay. So if we do that derivative, we get a CL alpha V, ZVS over U1, A to V, SV over S. Did I forget something? And again, the U1s cancel, which is nice, because this does not depend upon how fast we're going. But if you're Spider-Man, your spidey senses are saying, why the heck is there a moment arm in this CY derivative? Right? Why do we have a moment arm and it's just a force? Again, where did that come from? It's not the lag this time, but it's from the angle of attack generated by the P. So the P times that distance gave us that angle of attack that generated the force. So the vertical tail effect for the rolling moment and the yawing moment, you just multiply this thing times the appropriate moment arm, and you get that effect. Because, like I was showing you with the foam airplane, that's really what you're doing. Forget the wing, the horizontal tail. I'll get this thing rolling the right way. It's rolling this way. So we're getting a force this way that we just derived. And then we just multiply it by the x distance to get the moment arm, to get the yawing moment, and the vertical distance to get the rolling moment. So the effect is just multiplied by the moment arm to give you the effect for yaw and roll. So those are easy. So again, now we're still just talking about the vertical tail effects. So CLPV, the V is for vertical tail, so I guess we should put vertical tail here, is just ZVS over B. There's the moment arm for rolling moment times this thing. And then for the yaw, it's XVS. Well, we got to make sure we get the signs right. So is this thing creating a positive or negative? It's negative. Do we get a negative? We got a minus sign here. It's going to go up here. So it's going to be a negative rolling moment. How about yaw? Which way is this thing yawing the airplane? Let's put our airplane up here again. Side force this way. It's going to be a positive yaw. So we need a minus sign here that's going to cancel out with the minus sign here to give us the right yaw. And in the book, he substitutes this in, and the signs are all correct in the book. We did that. So this is the vertical tail effects on all three of the derivatives that we're talking about. Now we need to talk about the wing. So we said the wing doesn't do any side force. So what does it do to the rolling moment? Let's draw a picture. I'll make the wings bigger than what I had before. So now we're talking about CLP due to the wing. There's our wings. This is a front view. Positive roll, still that way. So let's look at the foam airplane. So here's our airplane. It's rolling like this. What's this wing doing relative to the air? It's going down, right? So it's going to be generating more lift because there's a relative wind coming up against that. So this is moving down. And this one is moving up. And if you grab this airplane and try to rotate it quickly, you can feel that resistance to the motion because the air is hitting the bottom of this and the top of this. So that means that there's an increase in angle of attack on this side and a decrease in angle of attack here, which means there's more lift and more drag and less lift and less drag on that wing. So over here we have a big lift vector, and over here we have a littler lift vector because of the roll rate. That difference is because of the roll rate. Otherwise, both lifts on both wings would be the same. So which way is the rolling moment generated? We've got an unbalanced force, right? So we get a negative CL due to the P. So the wing, a positive roll rate, produces a negative CL. The derivation to go beyond this, we have to know the lift distribution on the wing. And that gets pretty complicated. You got to divide it into strips and look at local angles of attack, right? Because the wing tip's going down a lot faster than near the root. And so you have to look at the lift distribution. Your book shows some pictures of that, but they're just showing how the lift distribution is higher on the left side than on the right wing than on the left wing. So if I ask you for an explanation of the rolling moment due to roll rate, this is what you would do. And it's physics and aerodynamics and moment arms, really, right? So this means that CLP is negative. Except if we've been a bad pilot. This is if the wing is not stalled. And why is that important? Well, here, if the plane starts to roll, this is going to stop the roll. That opposes the disturbance. So this is an important dynamic stability, is that it will stop a roll, just like you feel a resistance on the wing as you roll. But if why did I write this? If not stalled, why is that a big deal? So what happens to a wing that's stalled if you increase its angle of attack? Right, think about the lift curve when you're stalled. You're up in this region here, which means if you increase the angle of attack, I bet that's not showing up very well, is it? If you increase the angle of attack and that wing is stalled, the lift changes, gets worse, gets lower. Drag probably gets higher, but the lift goes down. And the opposite happens over here. If both wings are stalled and you do this, this wing will unstall, and you'll be back over here to where you're getting more lift than you were if you were stalled. You're up further up this way. So what does that do? It flips the whole thing around, right? So now, if you're stalled and you have a roll rate, you get a positive rolling moment due to roll rate, which makes you roll faster, which adds to the effect. P is rolling faster. You get more delta alpha over here, less delta alpha over here. You get an even higher rolling moment that makes you roll faster. What does that sound like? Sounds like you're rolling, right? What's it called when the airplane starts to roll in the air? And you're not doing it on purpose with a barrel roll. It's what? Well, that's the dynamics. I mean, it's called a spin, right? The airplane's spinning. And we'll find out that the same thing happens with yaw. So if the airplane's stalled, not only does it start to roll even faster, but it'll start yawing even faster. And that's why stall is a problem. I mean, the idea that you lose lift just means you start falling out of the sky. And if you can get pointed down, you're good. But if it stalls and then the wing drops and you start to roll and it rolls even faster and faster, that's what makes the spin dangerous, because this stability flips sign and your airplane doesn't want to stop rolling. It wants to roll even faster. Okay, how about the yaw? So this is a big we do care. We want this to be negative. And it almost always is, because of those big wings stick out there, unless we're stalled. Oh, how about the vertical tail effect? You go, well, that's still there, right? Because the vertical tail's not stalled. But if the wing is stalled, there's this huge wake coming back from the stalled, disturbed air. And so the tail becomes less effective because it's in this disturbed air in the wake of the stalled wing. So you lose that effect as well. How do you fix it? Power off, let go of the, like nose down and let go of the controls, right? That's what the dude in the aerobatics competition talks about. Did you guys, were you in 324 when I showed that video? So power off, nose down, and the plane will recover all by itself, hopefully. Now, if you're in a fighter aircraft that has marginal stability because of other performance issues, and you get into a really bad flat spin, then it may not recover by itself, which is what happens in Top Gun, right? So even a fighter aircraft, they try to test it enough so that they don't have those flat spin or unrecoverable spin modes. Now, if you're a good pilot and you can figure out which way you're spinning, gosh, I don't know, pilots help me out. You do opposite rudder to the way you're yawing, right? You do opposite rudder, power off, and stick forward, and hopefully you can recover. But sometimes it's hard to tell which way you're spinning when you're up in the air. All right, what's next? So fundamentally, don't stall the airplane, especially near the ground. So we did, oh, and this is the wing effect. Talked about the vertical tail, the horizontal, same deal. The horizontal tail is just another flying surface like the wing. How are we doing on time?
Yes, 506.
5:06, okay.
The exam next Tuesday.
What does the homework say? Oh, it's next Tuesday. Yeah,
And the homework saying next Tuesday.
the homework's due next Tuesday. So I'm going to go over the first two problems on the homework on Thursday so that you have feedback on those. So work those two by Thursday so that, because they may be on the exam, something similar to that.
So the exam will remain on Tuesday.
The exam is on Tuesday, yeah. And we're a little bit crunched because we're done with in-person exams by Thanksgiving. So I want to get these 4 exams in before Thanksgiving, and then we'll do a final online. All right, so now we want to look at the yawing moment due to this same effect here. So we're talking about CNP. We've already talked about the vertical tail, so now we're just talking about the wing. So what do the drag vectors do? Because it's the drag vectors on here that are going to cause the yaw. So we have a drag vector coming out this way, a delta drag, and then we've got a drag vector going into the board there, which is totally not right. It's the other way around. That's into the board. This is out of the board because we got less drag here, drags in that way. So it's a shorter vector going backwards, a bigger vector. Maybe a top view would help. So here's a top view of the same situation. I made these wings really long and thin, didn't I? So we have more drag on this wing and less drag on this wing. Less drag, more drag, right? Because we said there's more a positive delta drag and negative delta drag. And so this wants to yaw the airplane in the positive direction. So what that means is a positive roll rate will lead to a positive yaw if we're not stalled. Is that good, bad, or we don't care? So we've already said that CLP being negative is good because this stops the roll rate. But this says if we have a roll rate, we're going to get a yaw rate from the yawing moment. Is that good, bad, or we don't care? It's not a big stability parameter. And in fact, it's just kind of a side effect. But that's a coupling that could lead to problems because all we do is want to roll the airplane, but wow, it turns out we're also going to yaw it as well just due to this effect. So it's a side effect, it's a coupling, and that's what makes lateral directional dynamics more complicated than longitudinal. So the takeaways from this, we're talking about the roll rate. A positive roll rate, if the wing's not stalled, will create a negative rolling moment to stop the roll rate. We get that from the vertical tail, and we get it from the wing and the horizontal tail. We also get a side force, which is kind of a side effect, no pun intended. And then the roll rate will produce a yawing moment as well, so it will actually cause the airplane start to yaw. And so that's why if we're stalled and this flips around and you start to roll, and you start to roll due to the stall, it wants to roll even faster, and then that roll rate will cause a yaw rate, so you'll start to yaw at the same time. So that's why a spin is not just pure rolling, because the pure rolling gets coupled into the yaw, and the airplane will start to yaw around as well. There's a couple other really minor effects that your book talks about. One's called lift vector tilting, because with this angle of attack changing here, the lift vector actually tilts forward. And this lift vector tilts backward because remember, lift is perpendicular to the relative wind. So the relative wind here is coming in more from below, so the lift vector tilts forward. And that adds to this effect here. I'm not going to go in detail, just know that if you ever hear somebody talk about lift vector tilting due to roll rate, you can go, oh yeah, that's in my book, I can go look that up. And there's another thing called lift wingtip suction. Let's see, I flipped this around, didn't I? So let's get that back right. If there's more lift over here, you've got a higher pressure on the bottom than the top, so you get a wake vortex here. There's not as strong of a wake vortex over here because the lift is less. And so they say you can get some suction because of this flow, asymmetric flow around the wingtips. But again, that's a minor effect, and he talks a bit more about it in the book. But the big effect is the one that we've been talking about, the lift and the drag differences due to the roll rate. All right, so now we've done that column in the matrix. So the next effect is the yaw rate, R. CYR, CLR, CNR. And let me just introduce that with the foam airplane, and then we'll wrap that up next time. So now we're talking about the airplane spinning with a positive yaw rate, which is nose right, because z-axis is down, so we're talking about spinning like this. And you can look at the vertical tail, and you can see that it's sweeping through the air. I need my vector. So it's spinning like this. There's a relative wind coming in from this direction. So I get a side force on the vertical tail like that, which is going to stop that motion. So that's the vertical tail fin because it's aft of the center of gravity. It's going to be sweeping like that, like this, and I get a force like that to oppose that motion. So that's just pure stability. The yaw rate generates a force on the vertical tail that stops the yaw. But because the vertical tail sticks above the CG, that yaw rate is also going to roll the airplane. And there's that coupling again. And because we're spinning like this wing is moving forward, this wing is moving backward, and so we get more lift over here and less over here. So the wing is going to cause the airplane to roll as well because of the asymmetrical lift. And we get more drag here, less drag here, which is going to yaw the airplane. And we'll draw pictures about that next time. But that spinning effect, vertical tail, big player, wing is a big player for the roll and yaw moments. And you get coupling from that as well. So if the airplane is yawing, it's going to want to roll. And if it rolls, it's going to want to yaw. So they keep coupling back and forth. And that's how you get the Dutch roll mode, in addition to some side slip and everything else going on. And if the wing's stalled, you get the opposite effect. The weight comes back, affects the vertical tail. So maybe you don't get your yaw stability either. And so the roll and yaw rate keep coupling and increasing each other, and that's how you end up in a spin if you're stalled, because you lose that stability. All right, everybody go home, stay warm. I think it's supposed to rain tomorrow and wash all this stuff away. You don't believe it? It's Kansas.